looking at implications, right? So, and I said, so for implications, what you essentially have as the proof is a identity function, right? We want to prove P implies P. So we want to prove P implies P because we are operating in this world where we have Curry-Howard correspondence. Essentially, we have to provide an evidence for P implies P, and the interpretation of implication is just a function. So given evidence for P, we just have to return the evidence for P. And if you print P implies P, what you get if you forget the first argument, which is the, you can sort of think about that as the polymorphic type, what you end up getting is a evidence for P, and all this is doing is returning the evidence for P, right? And that's the proof for P implies P. Right? So let's keep moving on. So here is another, yeah, okay. So just to complete the story, so here is just the direct proof for P implies P. So the theorem is the same. As in, we are not writing it as a theorem, we are just writing it as a definition whose type happens to be the theorem, right? For all P, P implies P. And the proof is that you take the first argument P, which is this for all P, so that you get the type. And you get the evidence for P, you just return the evidence for P, right? And this is the same as what we had constructed using the tactics. Okay, so the point is, as the proofs get more and more complicated, we are not going to be able to write it directly, and tactics are a way to construct complicated proofs. Let's keep going along this path and look at more theorems on implication. So here is a syllogism, right? Assuming P implies Q, and you are given P, prove Q. So if you sort of ask the flip question, right? Write me a program that has this type. So you can sort of think about this as the higher order function that takes a P and returns a Q. You are given a P, and then you are returning a Q. So the higher order function is just function application. So this is the function argument, this is the value argument. You just apply this function on this value, you'll get the proof, right? And so that is the view of how to, that's the evidence, right? But how do we actually go ahead and prove it using tactics? So here is the proof. So the proof, once you start the proof, you get the same theorem underneath. You do the introductions. So I'm going to introduce PQ. The evidence for P implies Q, the evidence for P. So I just name it as PQ, evidence for P implies Q, and evidence for P. And the thing that we do here, right? So if you sort of stare at this, so this pattern is going to come over and over again in our proofs. So what we need to show is Q, right? And what we have is we have evidence for P, and we also have evidence for P implies Q, which says that if I have P, I can show Q, right? And the typical way we proceed is that we do backwards reasoning. We say, okay, I know that if I have P, I can give evidence for Q, and I need to give evidence for Q. So what you will do is you will apply backwards reasoning and say, instead of showing Q, I will actually show that I can give you evidence for P, right? And then that because of this P implies Q evidence there, we know that we can go ahead and prove the goal that we want to do, right? And the reason why it's called backwards reasoning is will become clear when we apply, when we see this new tactic. So we see this new tactic apply, which applies evidence for P implies Q on the goal, right? So what this means is that your goal is Q. I know P implies Q. So instead of showing Q directly, I'm going to show P, right? So that's the tactic that we are doing, and we are doing backwards reasoning because if you apply it, right? So observe that this Q is changing into a P, right? So that changes into a P because we are going to show P now, and P is directly in the assumption, right? So, and assumption makes it go through. This apply tactic will often use it, right? So we will often see that we will have a goal, and we have something that looks like some constraint, some proposition implies the goal, and all we do is saying instead of showing the goal directly, I will show that the antecedent holds, right? and we are doing backwards reasoning here. Right? So that's the reason why this proof goes through. And if you print this proof, you will see that it is just function application, right? So you have a function argument here, which is p implies q. You have the argument, which is p, and all we are doing here is applying this function on this value, right? So essentially, the same as what would have done in OCaml, right? If I were to ask you to write a function whose type is p implies q to take p, return q, this is what we would have done. And that is what we are doing here. Hi, Akash and Sriram. If you had missed a few previous minutes, the video is recorded, so you can go back and have a look. We've not seen much so far. Okay, so that is apply, and we can also use apply to do forwards reasoning, right? So here is the same theorem: p implies q to p to q, right? And I do the intros. So the thing here is I dropped all of the variable names, right? P, Q, EVP implies Q, and EVP. So intros, what it does is it goes through it goes through the goal, and then wherever you can do introduction, it goes ahead and introduces all the variables. So the introductions here are P, Q, P implies Q and P. It picks names automatically, right? So it says P, Q. And because these are sort of informative names, right? So this is an hypothesis that we are going to push up, and this is another hypothesis. So that's why if you look at intros, it names it as H and H0, right? So it starts with H, and then if you happen to instantiate another hypothesis, it is H1, H2, H3, and so on. So it is good to name things, but oftentimes we just go ahead because we know what is happening. So we sort of say intros. It will pick names for us, and we'll just use those names. So earlier we applied, so we used applied tactic to do backwards reasoning by applying it on a goal. But essentially, right, so if you sort of stare at these two things, right, you can sort of imagine there are two ways of reading these two, right? If we just look at the first one, it says that H is an evidence for the proposition P implies Q. The other way, the functional way of looking at it is H is a function whose type is P implies Q. And similarly, you have H0, which is P. So the thing is, you should be able to, if you just look at the functional way of looking things, this is a function, this is an argument whose type matches the argument type of the function. So you should be able to apply it, right? And that is precisely what we do for forward reasoning using the apply tactic here. So we are saying apply this function H in H0, right? So we are manipulating these terms, right? We are sort of taking it and saying to go and apply this function. So when you apply this function to P, this function P implies Q to P, you get an evidence for Q, right? And that is what we will see here. So you get an evidence for Q. So H0 gets transformed to Q. And once you have Q here, we need to show Q. So assumption will make the program go through. So I keep stressing upon this functional way of looking things. It is useful to keep this in the back of the mind. But as we look at more advanced example, we won't come back to this functional view, right? But that is what is happening underneath. So as long as you sort of understand that there are some basic principles with which these things work, some of the confusing things, right? You can always break it down to this functional view, and things will be very clear. Anyway, so one more theorem. So this says P implies Q to Q implies R to P implies R, right? And so this should hold, right? So I have P implies Q, I have Q implies R, and the way you should read this is you can read this as P implies R, right? So implication is right associative. So that's a natural thing. So that is why we can read it this way. And again, we are using variable names here. I'll just use the variable names. So we have PQR for this PQR, right? For all variables, we have evidence that P implies Q, evidence that Q implies R, Q implies R. right? So let's first introduce all of that. And then just to show that this is really right associative, if you sort of introduce all of this, right, we just have P implies R. So we could have moved this EVP to the first line. I just wanted to show it explicitly. So we have evidence of P as well. So how do you get this? So we need to show R, right? And we have these things as assumptions. So if you look at this, given P, I can go to Q, given Q, I can go to R and I can show this. Or you can do the backwards reasoning as we saw earlier, right? I need to show R. So instead of showing R directly, I will, because I have Q implies R, I will try to show Q. And once I have, so let's do that first. So I applied evidence of Q implies R, I get Q here. Now I need to show Q. I have P implies Q. Instead of showing Q, let me show P, right? Using this evidence P implies Q. So apply the evidence for P implies Q, you get P, and P we have an assumption, right? So so that goes through as well. So if you print this out, you will see that this is just the repeated application, right? So you have a function which is P implies Q, a function which is Q implies R, and you have a value which is P, and all you do is plug the right types in. So P implies Q applied to P gives you Q, and Q implies R applied to Q returns you R, and that is R. So I have the answer on the left hand side, but does this remind you of some function that we've seen in 3100? You want? No, this is just function composition, right? So you have two functions f and g, and we are sort of taking the input for f here, and then you get a result out whose result type matches the input type of g, right? And we return the result. So this is basically function composition, fgv, right? Yeah, so we've not, we might possibly not have named it explicitly in 3100, but this is quite useful, right? So if you have a function that adds something, increments something by something once, let's say I have suck, right, which is defined as um, x plus 1, right? And then I can do suck2 as uh, composition of suck, right? And if you, this is basically applying the function twice, right? And in Haskell land, they use this actual O as an infix notation. And the idea is that you're composing one function with the other. This is also related to the OCaml function that we've defined this way, right? If you remember, sometimes we've used something like this, right? F, G. That's the same as composition. Anyway, so these are all the same thing. So it's really nice that this function composition has an analog in the logic land, which is the fact that implication is transitive, right? So these are like nice ideas. I mean, you might sort of have seen this algebraic structure, right? They have some structure which is sort of common, and they are the same interpretation, right? Function composition is the same as implication being transitive. It's a quite a beautiful observation. Anyway, so we'll come back to implications again. So we've not seen how implications are encoded. They are actually encoded using simpler terms, but we'll come back to that later. Okay, so questions? Any questions before I just move on? Please do feel free to ask questions, right? I know you've been taking, I mean, this lot is sort of following up from morning full of classes for the undergrads. And so I know you might be tired, but if you don't understand anything, if you just skipped something, please ask, because it's a small class. Yeah, Sachin.
Casey, since we saw a couple of examples, would you mind going back and kind of informally describing the apply tactic once more? What it's supposed to do?
Apply is just a function application, right? So all we are doing, right? So apply, the easier way to look at apply is this one, right? So I have a function, right, which is h, whose type is p implies q. I have a value h0 whose type is p. So if you think about these as functions and values, you can apply this function on this value, right, to get the result of type q. And the interpretation in logic is that I have p implies q, I have p, so I should be able to show q, right? So, and that is done basically by application. And apply sort of informs, we are doing forwards reasoning here, apply sort of informs saying, take this hypothesis h, right, here, which is a function, and apply it in h0, which is the value. And if you take a p and apply to p implies q, you get something which is a q, right? So this is the result, and that has the type q, right? So apply is sort of doing just forwards reasoning, and apply is just functions, right? Function application. Backwards reasoning is sort of, I mean, a logical view makes sense here. So we are doing backwards reasoning here. So essentially, the way to read this is I need to prove R. And in my assumption, I have Q implies R. So instead of showing R, right, I'll just show Q. Because I have the evidence that Q implies R, I will show the goal anyway. So that is another form of apply for doing backwards reasoning. This is backwards because we are uh, we are applying, but going from R to Q, right? And we get a Q here. Similarly, for we need to show Q. We have P implies Q, and instead of showing Q, I'm going to show P. Why can I do that? Because I know if I get a P, I can always get to Q, get to a Q. Right? So that's the reason why we are doing this. Does that make it a little bit clear?
Yes, that was quite helpful. Thank you.
Okay, so forwards reasoning, it is better to look at it as function. Backwards reasoning, it's strange, right? Backwards reasoning, we don't apply functions backwards, but logical way of thinking about it makes sense.
Oh, and by the way, since you kind of used the analogy of a function, right?
Yeah,
Can we take it for granted that it will work for any kind of function and not just these logical ones?
that's it. There are,
It should, right?
yeah, it should, because implication is a function. So anywhere you see something that has like 7 implications, and then you have something which fills the evidence for the first one, you can always apply it. So that's yeah. So Coq, we are looking at simple tactics. Coq has some these auto tactics, right? Automatically prove certain things, and what they end up doing is, oh, I have this. I don't know whether something will lead to a proof. What I will do is I'll make sure to try different ways of applying things. As long as the type matches, I will see whether I can prove the goal. We will see more tactics like this later in the lecture. So we are looking at simple tactics, right? But as we prove bigger programs, proving everything in this methodical detail is not helpful, because we are doing very basic reasoning. We know this holds, right? So we should be able to use some of these ideas directly. And there, Cox's underlying mechanism for dealing with tactics allows you to build expressive programs that sort of says, I see a P implies Q, I see a P. Um, the uh, the programmer has asked me to prove something. Let me just apply it. Let me see if I can get to a useful point. And it does breadth first search up to some depth, and then comes back and says, okay, I proved it or not. We'll see all of this in later classes.
Sir,
Yeah, Akash?
uh, sir, I don't understand how in intros the different variables get assigned to different expressions.
Oh, okay. So what are all there, right? So we say there is a for all PQR, right? So, and whenever you have a for all, one way of looking at it is, I want to prove something that holds for all things. Instead, I will just pick an arbitrary thing. that has the type P, right? And I will prove it for that. This is so if you go back to your 3100 lecture slides, there is a for all elimination rule, right? That basically says this. So if you can show something holds for arbitrary element that has some particular type, then it holds for arbitrary then it holds for all things, right? Because we are not assuming anything on that for all. So essentially, we have 5 introductions here, right? And the first 3 are for these for all variables. So whenever we see a for all in the goal, we will always introduce them. We will say, okay, I'll just assume this holds for some arbitrary PQR. So when you do the first 3, all you get is we know PQR are propositions. We know nothing about them further, right? And those are 3. And we have 2 other things, right? And
So you are muted.
Casey, I think you went on mute.
yeah, okay. Can you hear me now?
Yes.
Okay. So yeah, so whenever you see an implication, the way to read this is some antecedent, this is some consequent, right? You can read this as A implies B, this whole thing. And intros also works for these implications. And essentially, it says that in order to prove A implies B, I will assume A and show that B holds, right? And that is the second place where intros holds. When you intros EVP implies Q, you are essentially taking the antecedent and moving it to the assumptions, right? That is the one. And there are 2 more here. The first one is Q implies R, right? That you can intros here. And once you do that, you are left with P implies R. Again, that is an implication. So you can do intros P. Why doesn't this work? Oh, intros. I'll just do intros because the name is clashing. So that's why it's not allowed. Does that make things clear, Akash?
Yes, sir.
Okay. So intros for now, the thing to remember is intros works on for all, intros works on implications. For all, it just moves the for all quantified thing to the assumption. And for implication, it moves the antecedent to the assumption. Okay. So let's delete this one and then continue. Okay. So we've seen this. Okay. So moving on. So conjunction, right? Um, so here is a simple theorem, right? So for all propositions P and Q, right? If I have P and Q, then it implies that P holds, right? So why do we think this is true? We know we have the evidence for both P and Q, right? So if I need to show P, I can just show you P. If I need to show Q, I can just show you Q. That's the understanding there, right? And our proof sort of follows the same lines of argument. So again, we start the proof. As I mentioned before, you don't need to give these arguments, but I'm just giving it here for clarity. So we introduce PQ and the antecedent here. So all 3 are moved to assumptions. So I have PQ and P and Q, right? So now the way to sort of um, proceed with the proof is using this different way of using a tactic that we've seen before. Okay, so let's just go along with the tactic now, and then we'll come back to how this actually works. So what I'm saying here is I know P and Q contains the evidence for both P and Q, right? So what I'm doing is I'm applying destruct tactic. So recall that earlier we had used destruct for case analysis, right? We said destruct list and we get a empty list and a cons list. What we are using destruct here is to destruct the 2 proofs that we have in the conjunction, right? And yeah, so the syntax is a bit weird. We will also come back to why the syntax is written this way. But all it says is when you destruct it, you get two things out, right? You get the evidence for P and evidence for Q. I'm just giving names for P holes and Q holes as informative names. You don't need these again. So when you destruct it, all that has happened is from P and Q, you've gone to two separate assumptions, right? That P holds and that Q holds. Okay, so now that you have a something that is an evidence for P, I need to show P. I can just appeal to assumption, right? It is there in the assumption. It has gone through. So that is how this works. This looks a little bit magic, right? So why should destruct work on this P and Q? What is so special? It used to work on just algebraic definitions, right? Last time when we had applied it, we applied it on a list, which was just a definition. Sorry, it was an inductive type. And what is happening here? So if you sort of dig in and see the proof for and first, which is the theorem that we just proved, right? We are going to print the proof, print the evidence for it. It looks surprising. So this P and Q proposition corresponds to the for all here, right? And it takes the evidence for P and Q, which is the evidence for P and Q here, right? And implication means this is just a function, right? So we are going to return a function. So this is the function. And what we are in fact doing is we are pattern matching on P and Q. That's surprising. Okay. We are pattern matching on P and Q, and there is some constructor conj, right? And what we are doing is we are somehow getting the first. It has two elements, right? Conj takes two arguments. The first one is P holes, and the second one I'm just using underscore so that I'm not explicitly naming it, but really that is Q holes, the evidence for Q holes, right? And I'm returning the P holes, which is what is required for proving this theorem, right? This looks familiar though, right? So if you sort of look at this, this is just a construction of a pair in OCaml, right? So you take evidence for say integer, which is just some integer one, say, and evidence for Boolean, which is say true, and you can put them together in a pair constructor, right? So you can write something like this. So I have one, which is an integer. I have true. So I'm writing OCaml. So this is an integer. This is a Boolean. And then when I construct 1 comma true, right, using this syntax, what I get is some int star bool, right? So this is so there is something, some construction going on, right? A way of putting them together so that you get this type. That is precisely what is happening here. So you get a P holes, right? And you get a Q holes. And the way of putting them together is this conj constructor. We'll see what conj is. And once you put that together, all I'm saying is, oh, now that you have a thing which has two things, of course, you can just call it as evidence for P and Q because you separately hold the evidence for both, right? This constructive logic is nice because you always have, when you say I have a proof for P and Q, you essentially have to have a proof for P and proof for Q, right, in hand. And conj is just like this pair construction thing, right? And that is just, we are just pattern matching on conj and getting the first element out and returning it. So this is interesting, but let's really look at what conj is and where it comes from and where it is defined, right? That sort of informs how conjunction is actually encoded in Coq. Conjunction is not a primitive thing; it is also just a data type, and that is what we are going to see. So what is conj? So conj is this constructor, right? That takes two propositions A and B and gives you this thing which it names as A and B, right? That is the proposition, which means both A and B holes, right? So again, this is just syntactic sugar. As we've seen before, in order to locate where syntactic sugars are, you use this locate command. If you locate it, Coq comes back and says, oh, whenever you see A and B, you have to read it as this type, which is and AB, right? So what is and? So and happens to be just a type definition, right? It is just so and is exactly the same as the pair type. What is a pair type do? Pair type takes A and B and then returns you a pair of A and B's, right? So and is a type that takes two propositions, A and B, right? And then says, okay, I am going to return another proposition, and there is only one constructor for and the constructor is conj. It says that given an A, given a B, I'll just return a A and B. This is exactly the same as this type which you can write. So sorry, type would be pair is P of star B, right? So I'm constructing a pair here with two values, right? Alpha and beta, and that is what is happening here as well. I mean, the syntax is a bit different. Of course, you can sort of name this pair as an and this p as a conj, right? And then if you write it in this GADT syntax, what you'll have is you'll have a quote. In OCaml, unfortunately, you have to write it this way, but yeah, you get a quote would be and it's same thing, right? So there is no difference here. All it is saying is whenever you see conjunction, right? It is just a plain old value, and the plain old value is constructed with this plain old constructor conj, which has two arguments. First one is the proof for the left hand side, and second one is the proof for the right hand side. And that is the reason why first one is the proof for the left hand side, right? And that is precisely the reason why we pattern match and then we return the proof for the left hand side. And that proves, I mean, that function that you construct here is actually the proof for how to go from P and Q to P. I mean, this is so simple that we've actually seen some of this in 3100, right? Not in such a detail, but we've encoded conjunction in simply type lambda calculus exactly the same way. So where were we? We are here. And you can do the same thing for the second one, right? So I want to show P and Q implies Q. So you do the introductions, right? And you do destruction of this P and Q. Again, destruct, you don't need to provide the names. Coq just picks you some names it thinks are reasonable. So it picks H and H0 hypothesis, and then assumption makes it go through. So we proved that P and Q implies Q. And if you look at the proof, it is what you expect, right? So I know P and Q value, right, has only one constructor, and that constructor is conj. And I know for a fact that the second argument of this value in this conj is the evidence for Q. So I'm just going to pattern match and return it. Right? So that happens to be the proof that we construct using these tactics. Questions on this before I continue with this? The high-level takeaway is this, right? The fact that you have a conjunction in the language in Coq is just the syntactic sugar over inductive data types. And the data type is very, very simple. It just takes two propositions and then puts them together using this conj constructor. And that's all there is going on. Of course, you want to manipulate this in some way, and we use tactics to destruct it. But the construction itself is very simple. Right? So here is another theorem. Right? We just want to see how to program with tactics using conjunction. So that's why I'm adding this very simple theorem. It says 42 equals 42 and 43 equals 43, right? We know this holds because equality is reflexive here, equality is reflexive here, and we are just putting together two things which we know independently hold, so it should hold as well. So how do you actually prove this? So the thing that we did here, right? We had a conjunction in the assumption and we had to use a destruct tactic to get two sub evidences that were present in the conjunction. But the difference here is we have a conjunction in the goal, right? So this is sort of different, right? Earlier we had two pieces of evidence that was just put together using this conj constructor. Here we need to show both of them independently hold. The obligation is on us to show that both 42 equals 42 holds and 43 equals 43 holds. We cannot destruct it because this is not a value, right? This is sort of what we need to actually prove. So the tactic that we use here is known as split. So whenever you see a conjunction, what split does is splits it into two subgoals. So we need to show both 42 equals 42 holds, 43 equals 43 holds. You apply split, you get two subgoals, each of which you proceed and prove independently. And here it is trivially true, right? And the same with the other one. So we just use trivial to make that first one go through, make the second one go through. Right. So the thing to remember here is the distinction, right? Whenever conjunction appears in the assumption, you have an evidence which has two sub evidences built in. So we destruct it to get the evidences. Whenever you see conjunction in the goal, it is completely different. Sorry. In that you have to show that both of them independently hold, right? And then so you split them up into two subgoals and you make it go through. Okay, so if you actually see what the proof is very simple, right? We know that the proof for 42 equals 42 is EQ-REFL, as we have seen earlier, and 43 equals 43 equals EQ-REFL. That is a proof for 43 equals 43. And we just use the conj constructor to put together both of the proofs. And hence you get proof for 42 equals 42 and 43 equals 43. Yeah, any questions on this?
Casey, the split tactic, right? Could you give us an idea on what kind of goals it works on? For example, here we saw it on a conjunction.
Yeah,
What
so
sort of
it works on conjunction, right? So conjunction is yeah. So if I'm not mistaken, so I don't know the precise answer to this. If I'm not mistaken, split only works on conjunctions, but I will confirm this later. So sometimes what happens is tactics are sort of very imperative programs. Their specifications are quite not easy to describe in a few words, right? They might do something interesting as well. So the way to learn the tactics is to sort of see patterns and know what tactics to apply, right? And you're asking a very valid question, but my answer here is know that split works on conjunctions. We will actually not use split a lot in some of the main bodies of theorem proofs we'll do. We will see a more expressive tactic that sort of does all of the low level that handles propositional logic directly. We'll see some of that later. But for now, imagine that split just works on conjunction. But I'll get you an answer in the next class for whether it works on something else. Okay. So one last proof on conjunction. So if you have P and Q, evidence for P and Q, then it implies that Q and P also holds. If you sort of imagine this as evidence, right? P and Q has two pieces of evidence. Q and P just simply reorders it, right? Swaps the evidences in this conj constructor. And if you look at the proof, that is precisely what it's going to do. It's going to pattern match, right? With conj P holds, Q holds, and it's going to swap it around and says Q holds, P holds. And you'll get evidence for this. But let's look at how the proof is done using tactics. So you introduce three things, right? P, Q, and P implies Q. P, Q, and P implies P and Q. Sorry, not P implies Q. P and Q. You destruct you destruct P and Q, right? Because that is part of the assumption to get the sub evidences that is there. You get an evidence for P and Q. And we also have conjunction here. So you split it so that you get two sub goals. And for both of the sub goals, right, both P and Q are part of the assumption. So just assumption makes it go through. So you can just do assumption on all of the sub cases, and that goes through. And the interesting thing is what we said earlier, right? So if you just look at the proof, it matches P and Q. You get evidence for P, evidence for Q, and then you just swap the evidences and put it back together using a conjunction. So H0 becomes the first argument and H becomes the second argument, and that becomes the proof for Q and P. Right, so that is how conjunction works. Let's move on to disjunction. Right. So, so this says that if I have evidence for P, then P or Q works. Right? We know this is true because we can, in order to show P or Q, we can always show P, right? And that is how we usually go about proving things. And this is precisely how we will go about proving this particular theorem holds, right? Again, introductions. I'm going to do all the introductions, right? So now I have a disjunction in the goal, right? If I have a disjunction in the goal, I can either show that P holds, right? Coq is asking us to prove P or Q holds. So I can either show this by showing that P holds, or I can show that Q holds, right? I can pick either one. And if I show that it holds, then P or Q holds. That's the assumption, right? And the way we choose which one to prove is by a pair of tactics, left and right. So left picks the left side of the conjunction as the one that you're going to prove. Right picks the other one. So when you do left, which is a new tactic again, P or Q just becomes P. So what you are telling Coq is, I know you want a proof for P or Q. I'll just show P. Right? Coq says, okay, go and show P holds. And that is just part of the assumption. So that goes through. So again, disjunction is not magic. Disjunction is also plain old algebraic data type, right? So if you print or left, you will see that what has happened is this for all PQ, you take an argument, and evidence of P, you just take it as P holds, right? And you somehow construct from the evidence of P this evidence for P or Q, right? And the way you construct that evidence is this using this constructor called or intro L, right? And that comes from the definition of or. Basically, what or intro L does is it sort of takes one piece of evidence and then puts it as the left piece of evidence in a conjunction, right? And the right piece could be anything at all. And similarly, there is a dual, right, which is or intro R. The last R stands for the right. And given a piece of evidence, it just says this piece of evidence is the evidence for something or this type, right? So that's the idea here. And let's actually see, again, go through the motions, right? So this is just syntax. So let's find out where the syntax comes from. So the syntax is actually coming from this data type called OR, right? So this type OR is there. So let's actually see what the OR intro L does. Or you can also do, yeah. So what is the OR type? OR type is also just a type, right? And it takes two propositions, A and B. And what it does is it has two constructors. Conj has exactly one constructor, and the constructor took two pieces of evidences and put them together. So what you have in disjunction is two ways of constructing evidence for R, right? If you want to show A or B holds, it can either be A or be B. And that is precisely what these two constructors are meant to give you. So or intro L takes evidence for A and then gives you evidence for A or B, right? That is what we expect. And or intro R takes evidence for B and gives you evidence for A or B, right? We have two different constructors for constructing left-hand side and right-hand side. right? So yeah, so you can print arbitrary things. If you print or intro L, you will get the same type definition, right? So this is this again. I think we saw this in 3100 as well in the symmetry type lambda calculus lectures, and we are repeating the same thing here. So we had in L and in R as the constructor names there, and we use R intro L and R intro R here. So okay, so using that, right, we can see we can prove certain things. So I want to show that P or Q implies Q or P. I mean, this is you should believe that this holds, right? If any one of these holds, you can always construct this proof, right? If P holds, then you can construct this one, or if Q holds, then you can construct this one. So let's look at the proof. So again, do the introductions, right? So P or Q is part of the assumptions, and Q or P is part of the goal. I want to show that Q or P holds. So the thing is, this is a disjunction, right? It is possible that P holds or Q holds, and and the fact is that now we need to show that this goal holds with for two cases. First case is one where P holds. The second case is one where Q holds. And because we know that P or Q, this thing is just a constructor, right? It's just algebraic data type. You can destruct it, and that's the reason why we can destruct these sort of things. So when you destruct P or Q, you get two subgoals, right? In the first subgoals, Cox says that assuming P holds, now give me the evidence for Q or P. So how do we do that? So let's zoom in so that we only focus on the first subgoal. Assuming P holds, how do I construct Q or P, right? I can pick the right term to prove. So right is P, right? And once you have P, you can just make it go through with assumption. And similarly, Coq also wants you to prove the second subgoal, which is assuming Q holds, right? Can you show Q or P? Yes, I can, right? So you just pick the left one in the goal, and then you go with the assumption. And if you print it out, you will see that all we are doing is exactly what we would expect, right? So I pattern match on P or Q. If it happens to be R intro L, right, you get one piece of evidence, make it the evidence for the right-hand side. And similarly, if it is the evidence for the right-hand side, make it as proof for the left-hand side. Evidence for the left-hand side, right? So we just swap the things over. We just swap the constructors, right? R intro L, R intro R. And that is the shape of what we expect to prove here. Okay. So that's one question, Vishnu.
So, is there any sort of ordering in the way in which Destruct does it? Like, would it have worked if we had said after Destruct it's left assumption and then right assumption?
Or, so the thing is, so when you destruct, right? So you get two goals, right? So I'm just focusing on the first one here. So when you focus on the first one, you can pick left here, but you cannot proceed, right? You cannot show that Q holds. So the order in which we are actually writing the proof is the order in which the subgoals are given to us by Coq, right? In the first subgoal, I have P, right? I need to show Q or P. I need to pick P, right? I need to pick the right one. Does that make sense?
Yes, yes. Yeah.
It is the order was chosen because Coq chose to align the goals this way, and that is chosen because Coq's definition of the type happens to be that way. Good question. So yes, okay. So let's prove something that involves both conjunction and disjunction. This is just a way to complete the circle so that we know how to operate with both conjunction and disjunction in the same theorem. So this is or disjunction distributing over conjunction, right? Here Q, PR, Q and R implies PRQ and PRR. So this is, we know this holds. How do we prove this? So you get this thing. So this is typically the procedure, right? So anytime you see for all this thing, you introduce all the variables, right, and the assumptions as well, right? So all of the things go there. So now we need to show we have, what do we have? We have P or Q and R. Cog is not drawing a parenthesis around here, but there is an implicit one around this one, right? So assuming that we have this, we need to show this one. So there are two subcases here, right? Essentially, you could choose to split this here or destruct it here. That order doesn't matter. But I choose to destruct this one first. So if you destruct this, you get two sub goals, right? One where P holds, another where Q and R holds. If P holds, what do you do? So I need to show that a conjunction holds, right? Because I need to show conjunction holds, I need to show that both of the subcases hold in this. So let's split it, right? So I'm just zooming into the first one. Let's split it now. So you get two more subgoals, right? That correspond to the two components of the conjunction. And now it's basically just methodical, right? So I need to show, I have P, I need to show PRQ. Pick the left one, assumption goes through. And the next one, I need to show PRR. Pick the left one, assumption makes it go through. Right. So then you have the other case where you have Q and R. We need to show that this thing holds. So destruct H to get evidence for both independently for Q and independently for R. And now we have to show conjunction holds. So we have to show both of the cases. So split it. So you get two subgoals again. And then zoom in, right? If you zoom in, we have evidence for Q, and I need to show P or Q holds. So Q is the right hand side. So pick the right one, and assumption makes it go through. And pick the, so again, we need to show, we have evidence for R, we need to show P or R. So that's the right hand side. So right and assumption makes it go through. And this might all seem elementary, right? But what we are actually doing is from first principles, right? We have a mechanized proof of this theorem holding. So it might not seem quite useful at this level, but as you build more complicated proofs, right? So the fact that you actually built a proof means you have this evidence in your hand, right? This is not like some logical argument with some hand waving. We actually have a program that is the evidence for this particular theorem holding. And if you sort of print this, right, print or histogram. The program is short enough. You could have written it by hand, but using tactics, it's much more natural. So it's a sort of saying tactics is what you will do when you are writing paper proofs, right? Consider this, consider that, consider cases, and so on. This evidence happens to be simple, but not all evidences are simple, as you'll see later. Okay, so this proof was a little bit tedious. We can make it simpler without using any advanced tactics by just using tacticals, right? So we have left assumption here, left assumption, right assumption, right assumption. So we can combine this using this tactical semicolon. So after splitting here, we do left and then do assumption, right? So we can use the tactical semicolon to say after splitting, you will get two subgoals. On that, do a left and then do an assumption, right? And yeah, after splitting here, we are doing right and assumption. So just do the same thing. So semicolon says on both of the subgoals, apply right and followed by assumption. So you can make the proofs a little bit shorter using this. Okay, we are way over time. So any questions on this so far? So these are all like not meant to be too tricky. What I want you to take away is the duality between the proofs and the functional the underlying functional programming, that is sitting underneath, right? So that's the thing that I want you to take away from this lecture. But also the fact that we are using these tactics, right, and operating with these specific tactics to construct these functional programs. And okay, so I think I'll stop here, and then we don't have much to cover in this next lecture. Rest of the lecture, and then we'll look at how to use induction. Induction is when things get real, so we can start proving. Induction is the first place when paper-based reasoning sort of falls down. It becomes much harder to provide paper-based inductive proofs. And Cork will assist you a lot in making sure that you don't make a mistake. We'll cover induction from next week. All right. Thanks very much, everyone.
Hello.
Yeah, Vishnu.
Sir, I didn't quite understand the difference between tacticals all and semicolons. Are they the same?
Yeah, they're similar. So when you do, so you could have done all here, right? So you can do a split here, right? When you do a split, you get two sub goals, right? In both of the sub goals, I'm going to do right followed by assumption, right? Assumption. I think I need to use semicolon here. So this makes it go through. Let's see whether dot works. Yeah, dot doesn't combine it. So the idea is that you do a split, right? You get sub goals, and all says that for all of the sub goals, apply this command, right? And the way of sequencing the command is semicolon, right? And when we actually use semicolon at split, right? What we are saying here is, I know split is going to produce two sub goals, right? That is what it is going to do, right? Split is going to produce two sub goals. And what semicolon implicitly says is, on each of the sub goals, apply the rest of the sequence, right? It's saying the same thing. We are just expressing it differently. Does that make sense?
Yes, sir. So both of them basically achieve the same thing, right? More or less.
Yeah, achieve the same thing, and we will use semicolon far more than all, because it turns out that semicolon happens to be much more useful in complicated proofs. We'll see some of that in the following lectures. Okay, good. Any other questions? Okay, good. In that case, thanks everyone, and then we'll see you next week. There is an assignment that has been released. It will only take you half an hour to finish that. Just finish that and upload it. Make sure any of the installation things are taken care of, right? You can ask questions on Slack, and I'll be hanging around there often. Okay, thank you. Bye bye.
Casey, I have a general question that's not related to the course itself.
Yeah.
So, is there anything to be said about the human readability of the code that we write here in Cork?
We don't actually care, right? So this human readability of the proofs that we. Good question. So does the tactics list of tactics that we write here need to be human readable? From a software engineering standpoint, yes, right? Because if you sort of say somebody else is going to develop this, sure. But really, I really don't care what this proof is, right? As long as I have the proof for the theorem, which means I actually have something in my hand, which I know is the proof. So you can view it in both of the angles, right? So yeah, so it will turn out that we will use some advanced mechanisms as we go along in order to make our proofs go through. I only care that my proof goes through, right? If I trust that the Cork system underneath is correct, right? When I have a proof for something, I really have a proof for something, right? I don't care how the proof was obtained, right? So, interesting question about proof organization, though.
So why I ask is in one of the earlier theorems when we saw the proof, right? We use I believe intros kind of. No.
Oh, intros, yeah.
I think either intros or destruct, one of them. So you use them implicitly, and then you ended up with H, H0, and H1, right?
Yeah.
So as a reader, and also before that, before I pose the question, those H and H0 kind of found their way into the proof itself.
Yeah.
Right, if you notice, right?
Yeah.
And then the only way as a reader I would know what H and H naught is if I was running it in an interactive manner and I was getting
Yeah.
that feedback from Coq. Right?
Yeah.
Otherwise, there was no way I would know what that is. So
Yeah.
that's where the question came from.
Precisely. That's the yeah. So it will turn out that as we go along, naming variables, right? We will not do that. So we will just leave it as implicit.
Okay.
Um, and that's for good reason, because you often know what is happening. It is the proof that matters, right? Um, very interesting, very wider question this one is, right? So if I just say I don't care how ugly my code is, my code for doubly linked list is correct, right? If I just tell you that one, I mean, what I would say is, how do you know that your code is correct? Because we don't know, right? So when you just write some code and see, it's not clear. But clarity and all of that sort of helps in understanding and convincing yourself informally that something is correct. But here, when you actually prove stuff, you have a proof, right? That the code does what the theorem says. So yeah, I think there is an interesting duality, but if you look at real proofs, it's hardly very readable.
So if you look at like a large piece of
Mm.
software like ComCert, right, which I believe
Mm.
has a couple of thousand lines
Yeah.
of code, how did those guys manage? Because I assume that is a distributed team for sure, and I assume these code
So
was
you
passed
don't
around.
actually read proofs, right? The unit of um, the unit of interaction is lemmas and theorems,
Ah,
right? So I will give you, Shashin, can you prove this theorem? I will make it admitted, and then I will assume that theorem holds, and in my lemma holds, and I will use it in my larger one. But really, I won't bother with looking. As long as you've given me a proof, I won't bother looking into it,
oh, okay. Oh, I
right?
got what you
So
mean. So it's like in Java or C Sharp, for example, you pass around interfaces and say, use it, don't worry about how it works.
yeah, precisely.
Something
But the
like that.
interfaces here are very precise, right? The
Right.
interfaces here are actually the theorems that you use.
Okay, that makes
It's
sense.
a very interesting question, Shashin. I wouldn't have thought about this.
Okay.
Uh,
No,
yeah,
because I come from a software engineering background, so I was
yeah.
trying to understand if there's a style that people expect the
Yeah,
code to
the
be
unit
written.
of distribution is lemmas and theorems. You can see larger ones, right? So they will say we have an abstraction. These interfaces, these functions are there. We also have these sort of proofs, lemmas on these functions. So if I have a list function, I have all these properties for lists. All of them have been proved. I don't care what the proof is, right? So as long as these things lemmas have been proved. Uh, Interesting question. Okay, sounds good.
Okay, sure. Thank you so much.
Yeah,
Right,
Sindhu
bye.
has
Thank you.
joined. Bye. Hi, Sindhu. So, uh, are you joining now? The class was at 12, or have you clicked the wrong link? Or can you hear me, Sindhu? No. Okay. Bye, Shriram and Vishnu. You don't have to
Sir,
stick around.
I just
Yeah,
have
yeah.
one last question. Like, will the classes be held from 12 to 1 every Thursday, or is it that's for today? Or?
Typically, we tend to have it at 12 to 1 every Thursday.
Okay.
Yeah. Yeah. So, what is the why? Why would you ask the question? Just curious.
Like, I wasn't aware that the class was from 12 to 1. It was one
Oh,
of my
okay.
friends who joined the course and then let me know that the class is from 12 to 1 and not 1 to 2.
Okay. So I thought it was 12 to 1 because this course is specifically the last time I ran it at 12 to 1. And I was told that because we have it in D slot with lots of undergrads, this would be 12 to 1. And that was the instruction that I was given. Uh,
I think that slot is actually 1 to 2, sir, like the D slot.
oh, really? 1 to 2?
Yes, sir.
Okay. Uh, okay. So you'll have some conflicts, right? So.
I mean, I'm not really sure. Like, I don't think there'll be conflicts. Like 12 to 1 is usually the lunch break timing. So
But I
this
don't want you
happens a
to,
lot.
yeah, I don't want you to skip over lunch, right? Because you might have something else after. Let me confirm this and get back to you, right? I don't want to get the times wrong. Sorry, Sindhu. So you might not be aware that the class was at 12 to 1. But I'll confirm this, Vishnu. Thanks for
Sure, sir.
bringing this up.
And I don't think this should be much of an issue like this. I mean, I've seen this happen like multiple courses. So like, if even if the lunch is, we can have the lunch from 1 to 2 probably.
Yeah, okay. I'm hoping that nobody has both the classes, right? Both 12 to 1 and 1 to 2.
Okay.
But
BTech has D slot from 1 to 2 and MTechs have D slot from 12 to 1 and the other
I
one
see.
lunch for both of them.
Oh, I see. Okay. So,
This is one of them.
okay. So what is typically done in these situations? Is it just the instructor picks a time?
Yes, sir. You can pick a time.
Okay. Would 12 to 1 be okay?
Yes, okay.
Okay. So let's just go with 12 to 1 then. I'll just send a message in Slack as well so that others will also know. We'll fix it at 12 to 1. 12 to 1 works better for me. Um, okay. Thanks for bringing this up, Vishnu.
Sure, sir. Thank you, sir.
Okay. Thanks very much. I'll see you next week. Bye bye. Have a good weekend.
Bye, sir.
Sindhu, can you hear me?